All right. Today's chapter 4, networking in Google Cloud. This is called building bridges. Networking in the cloud is more than just connecting machines. It's about secure, scalable, and reliable communication between applications, services, users, and data centers around the world. And this chapter will unpack the networking foundation of Google Cloud Platform, including virtual, virtual private cloud networks, those are VPCs, firewall rules, VPC peering, private Google access, and critical tools like load balancing, cloud CDN, cloud VPN, and cloud interconnect. So let's dive in. VPC networking. This is the backbone of Google's cloud communication. So this is the nerve center of cloud infrastructure, the virtual private cloud, or VPC. Imagine the VPC as your own private highway system within Google Cloud. It's complete with lanes, toll booths, and secure on-ramps. It's how your services, virtual machines, containers, and databases talk to each other securely and efficiently. While everything is virtual, the isolation and control are very real. VPCs let you segment traffic, manage IP ranges, route packets, and enforce security, all without laying a single cable. The global scope and regional precision. Every GCP project is provisioned with a default VPC, which you'll see here. All right? This is pre-configured with one subnet per region. This helps new users get started quickly, but also demonstrates a key GCP philosophy. Networks are global, but subnets are regional. This means your VPC spans the globe, while subnets, those carved out address spaces, are tied to specific GCP regions like US West 1 or Europe West 4. Let's go in here and look at that. So while you can route traffic between Europe and the US within the same VPC, the infrastructure still respects regional boundaries, giving you control over latency, availability, and data locality. And let's take a look. All right. So how do VPCs work in practice? Let's explore some fundamentals of VPC behavior. They are unicast only. This means GCP's VPCs support IPv4 unicast traffic, which means point-to-point communication only. No IPv4 multicast or broadcast traffic is allowed. However, IPv6 addresses can reach IPv4-based VPC resources using translation methods. There's intra-VPC communication allowed by default. Unless you apply firewall rules, any two resources, say a VM and a container in the same VPC, can communicate freely using their internal IPs. Firewall rules are king. They determine which traffic is permitted to flow between resources, even inside the same VPC. Why this matters. The VPC setup provides flexibility and scalability. You can launch a VM in one region and access data in another via internal IPs. You can use a single network policy across a fleet of microservices. You can integrate hybrid networking setups with on-prem environments via VPN or Interconnect. So for the exam, note that VPCs are global constructs, but subnets are always regional. You'll often be tested on this nuance, especially when dealing with cross-region architecture or peering. So what gets deployed in a VPC? Almost everything. Compute engine VMs, GKE nodes and pods, Cloud SQL instances with private IPs, Cloud Run, especially when using VPC connector, serverless VPC access. Even App Engine and Cloud Functions can route traffic through your VPC, depending on your configuration. In essence, the VPC is your digital data center backbone, the layer beneath your applications that keeps everything connected and secure. So how does this all work? VPCs operate using Google's Andromeda Network Virtualization Stack. This allows Google to offer custom routes and firewall policies, live migration of VMs, flexible load balancing, and support for hybrid networking. You also get symmetric traffic routing, a major requirement for stateful firewall and intrusion detection systems. And remember, every VPC resource is bound to a single project, right? But you can share VPCs across projects using shared VPC, which we'll cover later. So to recap the behavior of GCP VPCs, let's summarize this as they are global VPCs with regional subnets. They're unicast traffic only via IPv4. There's internal communication by default, unless restricted, typically through firewall rules. There's granular control via firewall rules. Default VPC is auto-created per project. And you can create custom VPCs with full IP and route control. Now into subnets. Subnets are an integral part of your VPC. Let me see if I can find this. I'm not seeing it. Oh, why am I not seeing this? It should be on IPs, shouldn't it? Okay, we'll continue. So let's continue the journey to the architecture of this by talking about subnets, right? Let me look in the, oops, oops. No, it'll be here. Okay. So if the VPC is the backbone, subnets are the branches. These are precisely carved out IP address ranges that give structure and boundary to your Google Cloud resources, right? A subnet or a subnetwork lives within a specific region. And every compute engine VM, Kubernetes node, or serverless VPC connector needs to be attached to one. Subnets define IP scope, routing domains, and access control at a regional level, which is essential for availability, latency optimization, and network segmentation. All right, let's go down here. There we go. Here's where you see the subnet information. Okay. So when you create a new VPC, Google Cloud gives you a choice, or in some cases makes it for you. There's auto mode. In auto mode, Google creates one subnet per region automatically with pre-assigned CIDR ranges. This is for simple multi-region applications or for teams just getting started. But here's the catch: you don't control the IP ranges. So if you need to design a network with tight security, hybrid connectivity, or custom address planning, this won't cut it. That's when you go to custom mode, right? Custom mode, you get to define everything, which regions to use, what CIDR block to assign, and when and how to scale. Custom mode is the go-to for enterprise-grade environments, especially when dealing with overlapping IPs, shared VPCs, or on-prem VPNs, right? For the exam, remember, once you switch a VPC from auto mode to custom mode, you cannot revert it. So choose wisely, especially if you're planning for growth. Okay, so you would define the subnet here, describe it, select the region, and then select the type of IP you're going for. Typically, IPv4 is good. All right. So regional awareness. Each subnet belongs to a region, not a zone. But VMs, your compute instances, are zonal. So when you launch a VM, you need to specify the zone, like US Central 1A, the network, your VPC, the subnet within the selected region. This enables fine-grained placement of compute resources while still benefiting from centralized network control. Why subnet design matters? Subnet design is just an infrastructure task. It impacts cost, performance, and security. You want to isolate backend systems from public-facing services. Use subnet, use separate subnets with targeted firewall rules. You need redundancy, deploy subnets in multiple regions. You're planning a hybrid cloud, use custom CIDR ranges that don't conflict with your on-premises IP space. Remember, routes and firewall rules are scoped at the VPC level, but subnet boundaries determine where traffic can flow internally by default. Let's just go set that. Set a US East 1 IPv. Let's say 10.100.0.0-20. And okay, quotas and limits. As your infrastructure grows, you want to understand the guardrails in place. Here's some VPC subnet limits to keep in mind. VP net, six, wait, I think it's, no, 5 VPC networks are allowed per project. 7,000 VM instances per VPC network are allowed. And VM instances per subnet, there's a separate limit, which means while you're limited in how many VPCs you can create, subnets can support a massive number of instances, making them ideal for scalable deployments. Okay? So to recap, let's bring it all together. Subnets are regional, VPCs are global. You can choose auto or custom mode. You cannot revert from custom to auto. VMs need a zone, network, and subnet. Careful IP planning prevents conflicts in hybrid and multi-region scenarios. Okay. IP routes and traffic flow. All right. So let's now explore the circulatory system of your VPC, how traffic actually flows through your network, where it goes, and how it gets there. At the core of this movement is the concept of IP addresses and routing, essential knowledge for any cloud architect building scalable and secure systems on Google Cloud. So external IPs, these are public access with control. In Google Cloud, resources can have internal or external IP addresses. An internal IP is for communication within the VPC or connected private networks. An external IP enables public access to a resource, like a web server or a public API. These external IPs can be ephemeral, meaning they're assigned at runtime and released when the resource stops, or static, which means they're reserved in advance and bound to the resource a long time, right? Static IPs are essential for DNS mapping, third-party integrations, services that require a consistent endpoint, such as payment gateways or firewalls. Routing, the VPC GPS. Let me go over here and show you this. Okay. Okay, let's go over here. Routing. Okay. So actually, let me continue. Let me create this network real quick, just to give you an example. Just shows Kubernetes. It's a custom. I have the subnet. This goes Kubernetes 1, the region, US East, all right, US Central 1. That's going to be your main one. All right, 10.100.0.0/20. All right. Flow logs off, off, off. Let's add a subnet. Kubernetes. Because we already have this subnet. Oops. Oh, 2. Oh, US East 1. All right. 10 dash. Oops. 10 dot. What do we do? 10.100. Okay. 10.102.0.0/20. Okay. And then firewall rules. We'll apply these. ICMP, ingress, ingress. All right. This will be set as regional, regional, firewall configuration, policy, none. And then create. Okay. So routing, the VPC GPS. Every routing, this is creating. So we'll see that in a few minutes pop up. All right. The VPC GPS. Every VPC comes with a set of routes. These are rules that guide traffic through your network, like lanes on a highway. By default, every VPC includes a default route to the internet targeting all 0.0.0.0/0 traffic, which means any IP, and points it to the default internet gateway. This allows outbound internet traffic for VMs with external IPs. And then a local subnet route. This enables communication between subnets within the same VPC. Even if they're in different regions, this is key to Google Cloud's global VPC availability. Let's see. Custom static routes. Sometimes you'll need to override. Let's see. Mhm. Oh. Sometimes you'll need to override the defaults. For example, if you're creating a hub and spoke network or routing through a third-party appliance for inspection or logging. In these cases, you can define custom static routes by specifying a destination IP range, a next hop, like another instance, gateway, or VPN tunnel, or optional priority level. But be careful. Google Cloud will automatically disable any route that conflicts with an existing subnet's IP range. This prevents black holing yourself and your traffic by mistake. So route priorities. In GCP, route priority is a number set from 0 to 65,535. So 65,535. And here's the rule. The lower the number, the higher the priority. So 0 is highest, 65,535 is the lowest. So a route with 100 will override a route with a priority of 200 if they both match a given destination. This allows for advanced route control, defining a failover route that only activates when the higher priority route is removed. So real world examples. Let's look at how this works in practice. Okay. If you deploy a VM in US Central 1 and assign a public IP, thanks to the default route, it can reach the internet immediately. You can then create a custom route. Oh, oh, I must have done it. Oops, I did that wrong. I thought I did that. Interesting. Okay. Okay, so let's say you deploy VM in US Central 1 and assign a public IP. Thanks to the default route, it can reach the internet immediately. You then create a custom route to enforce traffic bound for a specific subnet, say 10.0.0.0/16, through a cloud VPN tunnel to your on-prem network. You give this route a priority of 50. Finally, you want to override that route only temporarily, so you can create another static route to the same destination with a priority of 10. The new route now takes precedence. All right. This kind of dynamic route manipulation is powerful and often shows up on the exam, especially in hybrid networking scenarios. So to recap, GCP assigns routes to direct traffic inside and outside your VPC. External IPs are needed for public access, but best used sparingly for security reasons. Mhm. Oh, well, that one got trashed. I'll create another one in a second. Routes control class traffic flows, and you can define your own. Route priorities help you manage traffic precedence. Google disables conflicting routes automatically to protect your networking tunnel integrity. Excuse me. Understanding this flow, how resources talk to each other, and how the internet talks to them is fundamental to building secure, performant, and resilient cloud systems. Let's try this one more time. Kubernetes, custom, Kubernetes, central one, IPv 10. Let's try 10. Just allow all of these. So these are the different protocols: custom, ICMP, RDP, SSH. All right. All right, we'll try and create that. We'll keep going. So firewall rules. The security at the network layer. All right. Go to the firewall. So let's imagine a cloud network, fully open, no barriers, no safeguards, every VM, every service, every packet of data, free to travel anywhere. That might sound liberating, but in reality, it's a security nightmare. That's why firewall rules come into play. In Google Cloud Platform, firewall rules act like the security guards of your virtual cloud, private cloud, allowing or denying traffic at the network level, but applying directly to VM instances. And here's the key. They operate at layer 3, the network layer, and layer 4, the transport layer of the OSI model. And they managing access based on the IP addresses, ports, and protocols. So they're stateful by design. All right? Firewalls in GCP are stateful. That means once a connection is allowed in one direction, say ingress, inbound from an external resource, GCP automatically allows return traffic egress for the duration of that connection. So you don't need to define both sides of a two-way connection. Only one rule is enough to open a secure session. They're IPv4 only for now. At Firewall, all firewall rules apply to IPv4 traffic only. IPv6 is supported for accessing IPv4-based VPC resources, but it doesn't yet have the same firewall management granularity as IPv4. So when crafting rules, especially for exams, assume IPv4 unicast traffic unless otherwise specified. Default rules, what's built in? Every VPC in Google Cloud starts with two foundational firewall rules. An implied egress allow rule. That means by default, all outbound traffic from a VM to any destination is allowed. An implied ingress deny rule. This blocks all inbound traffic unless you specifically allow it and explicitly allow it. And here's an exam tip, right? These default rules cannot be deleted and always have the lowest priority, set to 65,535. That means any rule you create will override them as long as its priority is set to a number higher, or excuse me, lower than 65,535. So if you set it to 1, it overrides it. 65,534, it overrides it. Okay? Predefined rules. Let's go back. Yeah, we got some good stuff here. Okay, to make your life easy, GCP provides a few default allow rules to enable basic functionality. All right. The default allow internal, right? It's this one. Okay, this allows communication within the VPC using IPv ranges 10.128.0.0-9, right? A default allow SSH, right? That's this one. This enables SSH access to port 22. It's useful for managing Linux VMs, right? You have the default allow RDP, which is this one. This is for remote desktop protocol, port 3389. This is typically for Windows instances. And the default allow ICMP. This lets instances respond to ping requests, which is great for basic reachability checks. These are enabled by default in default VPCs, but in custom VPCs, you'll need to create similar rules yourself if needed. All right. Some traffic is blocked automatically. Regardless of your firewall configuration, this is essential for cloud hygiene and abuse prevention. Block protocols and traffic types include GRE. This is used in some VPNs, but disabled for security and complexity reasons. Any protocol other than TCP, UDP, ICMP, or IP in IP. SMTP egress on ports 25, 465, 587. This is blocked to prevent spam abuse from compromised instances. These restrictions can't be lifted, even with the custom firewall rule. All right. So this firewall rule anatomy. All right. So let's break down what every firewall rule contains. Direction. Is it ingress, incoming traffic, or egress, outbound traffic? Match conditions. What IP ranges, ports, and protocols does it apply to? Target. Which VM instances are affected? You can match by network tag, by service account, or all instances. Action. Should the rule allow or deny traffic? Priority. A lower number means higher priority. For example, priority 100 overrides 500. Enforcement state. You can disable a rule temporarily without deleting it. It's useful for testing configurations safely. Okay? So these are, let's go. So let's see if I can find this. Okay, so scope the service accounts. Unique capability in VCP, you can scope firewall rules to apply only to instances using a specific IAM service account. This is a powerful pattern for least privileged access. For example, allow port 443 access to any VM running under the web-server-sa at project.im.gserviceaccount.com service account, right? This ensures that your security posture is tied to identity, not just tags or IPs, and it reinforces Google Cloud's identity-first architecture. So the final thought. Design like a security architect. Firewalls in Google Cloud aren't just guardrails, they're a critical design layer. They protect your workloads, right? They ensure only necessary communication is allowed and prevent misconfigurations from turning into vulnerabilities. Whether you're designing a zero trust network, building out a multi-tier app, or configuring isolated environments for compliance, firewall rules are the first and sometimes only line of defense. All right, so VPC peering. All right, so now that we've explored the firewall foundations of a single VPC, let's zoom out and ask a bigger question. How do you securely connect two separate VPC networks, maybe even across different projects or organizations without exposing data to the internet? The answer is VPC peering, a powerful capability that lets you link the networks directly over the Google's private fiber backbone. So let me do a little bit of, okay, all right, this is up. All right, let's see what this one. I'll make this, let's try to make this. Let's call it just Jules Docker here. And wait, um, so Asia Northeast 1 and 2.0.0.0/20. Wait, what did the RFC? Yeah, specs. Yeah, 192.160. Oh, yeah, okay, sorry about that. This would be 68. I'll allow all of these. Legacy. Okay, this will be good. Okay, so we'll have these. Okay, and this will create this network. So we'll have the Docker peer, we'll have the network, the Kubernetes network. So we'll go back to this. So VPC peering enables two virtual private clouds to exchange traffic using RFC 1918 private IP addresses. This would be, like we just showed here, the 10.0.0.0, right? Or the 172.16.0.0, or 192.168.0.0, right? The best part, there's no need for external IPs, no VPN tunnels, no NAT configurations, and absolutely no public internet exposure. This is cloud native private to private communication, right? So VPC peering supports traffic between projects in the same organization, projects in different organizations, and even different billing accounts, as long as permissions are in place. It's also compatible with many GCP services, including Compute Engine VMs, App Engine flexible environments, Google Kubernetes Engine workloads, and Cloud Run VPC connected services. This makes peering especially useful for microservice architectures, multi-project isolation, or shared networking patterns. Why would you use peering? Right? Let's break down the core benefits of VPC peering. There's no egress cost. Unlike external IP communication, peered VPCs exchange traffic for free within the same region. There's low latency, so traffic stays on Google's internal network, and there's no hop through the internet, which means less jitter, faster speeds. There's tighter security, so by keeping everything within the private IP space, you reduce your attack surface and avoid exposing workloads unnecessarily. So VPCs, peering rules and design considerations, like any powerful networking feature, VPC peering comes with a couple of guardrails. So let's walk through the key design rules. There's bidirectional configuration required. Peering is not just a one and done. To establish a connection between a VPC A and VPC B, both sides must initiate a request, accept the request, and only then is the peering active. No overlapping CIDR ranges. That's why I showed you here. Don't see them here. Maybe internal ranges. Well, you saw me set these up. Okay, so let's see. You show me a 10.0.0.0, and then uh, 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 oh, subnets. That's right. Okay, 192.168.0.0. See? And this is one. I'll probably try and do this here. Okay. So there's no overlapping SATA ranges. This is a big one. You cannot connect two peers. You cannot peer two VPCs that use overlapping IP ranges, right? So I showed you the 10.0 and I showed you the 192.168. If you have these as the same 10 dot and 10 dot, the peering will fail. So plan your IP space carefully, especially in multi-team or multi-region environments. One VPC can peer with up to 25 others. Each VPC can maintain up to 25 peering connections, which is generous, but it also means you need to think about your networking architecture at scale. Some organizations use a hub and spoke model, so there's a central VPC that manages shared resources and services and routes, and then there's spoke VPCs that are peered with the hub, but not with each other, right? And there's no transitive peering, right? So this catches a lot of people off guard, and it's a common exam topic. Let's say VPC A is peered with VPC B, and VPC B is paired with VPC C. Can A talk to C? No. Transitive routing is not supported. Peering relationships are point to point only. So if you need to talk to A, if you need A to talk to C, You must peer A directly with C. All right. Traffic respects firewall rules. Once a peering is active, firewall rules still apply. So if you want a VM1 and VPC A to connect to VM2 and VPC B, you must allow all ingress traffic on VM2, ensure egress is permitted from VM1, and verify both are reachable using their internal IPs. There's no magic shortcut here. Peering creates the path, but you control the gate. And VMs can have multiple NICs. So each virtual machine in GCP can have multiple network interfaces, or NICs, allowing it to connect to multiple VPCs. This is useful in hybrid networking scenarios such as a VM acting as a middle tier proxy, a multi-zone failover acts across peered VPCs, or security appliances spanning environments. But remember, only one NIC can be used for metadata server communication, which affects identity, access, and API calls, right? Wrapping up, peering with a purpose. VPC peering is simple to set up, but strategic in impact. Use it when you want low latency, secure communications across VPCs without the complexity of costs or external networking solutions. For mission critical services, interdepartment networks, or shared infrastructure patterns, peering is a best practice tool in your GCP networking toolkit. All right, so let me add peering connection. To this one, import, let's create, and then so add peering. Oops. We should be set up a connection to this VPC. There it is, active. And there it is, active. So this is my network to the peered network, and this is the project ID, right? And the status is active. This is very simple because it's in the same project and in the same network, right? So Kubernetes. Okay, so let's go back and see. So this is my network is Docker, just rules Docker over here, just rules Kubernetes, and it's peered with Docker. See this is Docker peered with Kubernetes. Project ID, just rules Kubernetes, which is this one, right? Just rules Kubernetes, active IPv. So these can communicate now, and they're good to go. So I'm going to go ahead and delete these. Well, I'm going to leave them going. I'll delete them at the end. All right, so next up, internal API access, private Google access. Imagine this. You start up a secure environment in Google Cloud. Your virtual machines live entirely within private subnets. There's no external IP assigned, and by design, your instances can't reach the public internet. But here's the dilemma. Your application still needs to pull from the Google Cloud APIs, maybe to write logs to cloud logging, store backups in cloud storage, or run a query in BigQuery. How do you make this happen without punching a hole in your firewall? That's where private Google Access step in. It's a subtle but powerful feature that enables private connectivity to Google's APIs and services without ever exposing your resources to the internet. Let's get this. Why do I want to see this private? Is it now Private Service Connect? Oh my gosh. Private Service Connect, I guess. Yeah, I guess that must be it now. Okay. So at its core, private access allows internal only VMs, those without external IPs, to access cloud storage, BigQuery, Cloud Spanner, cloud logging and monitoring, and Google APIs. You know, the ones that go with the .googleapis.com address. All of this happens over Google's internal network using your VM's internal IP. You can think of this as a secure gateway to Google Cloud services without needing a public-facing identity, right? So how does it work? Here's the architecture in plain terms. Your VM lives inside of a VPC subnet, and it doesn't have a public IP. The DNS resolution still points to the same API endpoints like storage.googleapis.com, database.googleapis.com, et cetera, et cetera. But when private Google access is enabled, that API traffic is routed through a private back channel instead of going out to the internet. This lets your VM access essential services like storing app data or pushing logs without compromising security posture. It's a zero trust cloud native approach to service access, right? Enabling this. So open the VPN network section of the console. Let's see this. VPN network. Select your subnets. Let's see. Oops. Should have done that. Subnets. Okay. And toggle private Google access. Let's see. Why don't I see this? Oh, there it is. Uh, I should be able to. Why am I not able to add this? I probably had to update this. Let me see. If I add a subnet, private Google access, boom. That's where I would do it. Okay. I should have done this when I created the actual subnet. So remember to do this when you add the subnet, because I don't think you can do this unless you delete the subnet and re-add it. If I created another one without an interrupting or intersecting VPN or subnet, then I could create that. So remember that you do that there. So you can't necessarily do it in medias res. All right, once enabled, any instance without public IP in that subnet can now call Google services safely and securely. So here's another prerequisite. The internet gateway route. So here's one subtle but critical requirement. Even though the VM doesn't use the public internet, private Google access still relies on a default route to the internet. Why? Because Google's routing logic still needs that default internet, that default gateway 0.0.0.0/0 in place to determine how traffic flows. Think of it as a logic path, not a public route. If that route doesn't exist, private Google access won't work. So for the exam, this is a common question. You must have a default internet gateway route, even when using only internal IPs with private Google access. When should you use private Google access? Let's walk through a few common cases, right? Security critical deployments. You're working in a regulatory or compliance heavy environment. Think HIPAA, FedRAMP, PCI, or internal zero trust networks. Private Google access allows you to consume Google services without ever allowing egress to the public internet. You want to restrict public IP usage. You want all compute nodes, including GKE or compute engine, to avoid external IPs by default. Private Google access gives them the cloud connectivity they need without public presence. Hybrid or service-to-service patterns. You've got workflows in Cloud Functions, Cloud Run, or App Engine, and your backend services live in private compute engine networks. Private Google access ensures they can communicate with logging, storage, and metric services to complete the observability loop securely. So here's a recap for the exam on the cloud. All right. VMs without public IPs. Right? This is what it applies to. The level of configuration is at the subnet level. The DNS resolution is the same as normal APIs. It requires default route to the internet. The traffic exposure stays internal to the Google's network, right? But in the use case would be something secure for access to Google's APIs from a private compute, all right? And for even greater control, just remember this. Combine private Google access with VPC service controls for data exfiltration protection, custom DNS to restrict or reroute Google API calls, firewall rules to enforce policy-driven API traffic access. Together, these features provide a tight, secure envelope for cloud-native applications that operate entirely inside your private networks, yet still need to reach the cloud's powerful managed services. Okay. Okay. Now we're going to talk about load balancing. Let's see. Okay. All right. So load balancing in the digital services, in the digital world, your services don't sleep. Neither should your infrastructure. Right? Imagine this. A sudden surge of traffic hits your application. 1 minute you're serving a dozen users, and the next minute 1,000. You need infrastructure that can scale up instantly, direct traffic intelligently, and protect your systems from overload. That's exactly what Google Cloud load balancing is built for. What is this? It's a global traffic manager. Unlike traditional on-prem load balancers, GCP's load balancers are software-defined and fully distributed. There's no single choke point, no box to manage, and no limit to where your traffic originates. GCP load balancing is fully managed, integrated with auto-scaling, and capable of handling millions of requests per second. It monitors health, routes traffic based on policy, and scales dynamically, all without manual intervention. Whether you're serving web apps, APIs, games, or large-scale analytics, Google's load balancers ensures that you can connect your users to the fastest, healthiest backend, no matter where they are in the world. What makes GCP load balancing unique? Let's break down what makes this approach different. Global and regional support. Choose a global load balancer to serve users across continents or a regional one for internal workloads. One Anycast IP. For global traffic, a single IP address is what you need. Auto-scale integration. Instances automatically come online or offline based on load. Cross-zone load balancing. Even traffic within a region is distributed for resilience. Built-in DDoS protection. So this automatically helps defend against volumetric attacks. This isn't just a tool, it's your cloud's air traffic controller. So there's types of load balancers in Google Cloud, right? Okay. Okay, so these are tailored for various use cases, but let's go through them. All right. There's the HTTPS load balancer. This is the global. This is Google's flagship layer 7 load balancer. It's built for high performance web applications. It routes based on URL paths, host names, or headers. It integrates with Cloud CDN for caching at the edge, and it supports SSL offloading, backend health checks, and geographic routing. Specific use case would be delivering responsive websites, APIs, or mobile backend services to global users from a single IP. There's a TCP proxy load balancer. This is also global. This operates at layer 4 and handles TCP traffic, which is useful when you want stream-based communication with a global reach. So this encrypts and terminates SSL at the edge. It's great for legacy applications, game servers, or custom TCP protocols. So you can think like financial applications, database front ends, or games with regional backends and global users. Okay. Another one would be an SSL proxy load balancer. This one is like the TCP proxy, but designed specifically for secure SSL traffic. It terminates SSL at the edge. It routes based on port 443 traffic. It's ideal for HTTPS apps without layer 7 needs. So a use case would be hosting an encrypted service that doesn't require content-based routing. Okay. Then you have the internal load balancer, right? This is designed for traffic that stays within a region. This load balancer is ideal for microservice communication, data pipelines, or batch jobs. It does not expose any public IPs. It balances traffic between VMs or containers, and it's common in private service meshes, or hybrid environments. So a specific case would be a backend service accessed only by internal components with no internet exposure. All right. So you can see this broken out on the screen. Application network would be the prompt. And you see this, the HTTP, the TCP, UDP, SSL, right? And you have the proxy. Is it going to pass through? So let's go. Let's just select this, just to select this. Is it going through the internet, the VPC, internet, going for TCP load traffic for a hybrid backend, or is this going to be proxying the traffic to the backends, right? So the IP source will be here, okay? Is it going to be public facing? Is it going to be internal only? So they simplified this in the Google Cloud GCP GUI, but my descriptions were accurate. Oh, and the final one, the external load balancer. Sometimes you don't need global coverage, just a regional internet-facing load balancer. This is for services that live and serve within one region. This will handle HTTPS, SSL, or TCP traffic. So this would be like a region-specific marketing app or a localized customer portal with compliance requirements. So to break this down, you're going to look at the backend configuration, which is where it's going to be routed to, right? You're going to look at this is where you define the resource group the traffic will be routed to. You can choose instant group, serverless neg, which is a network endpoint group for Cloud Run or Cloud Functions, or storage buckets for static sites. Apply health checks, right, to ensure traffic only reaches healthy instances. And you set up the host and path rules. This is your traffic policy. You can route, let's say, example.com/API/star, right, to one service, and then set it to example.com/static/star to another, right? So you use rules to fine tune how traffic moves between microservices. And then you have a front end communication. This defines how the world sees your service. This is going to be, are you going to assign an IP address, right? Is it going to be static or ephemeral? Are you going to choose a protocol, HTTP, HTTPS, TCP, or SSL? You're going to set port configurations and security policies. So load balancing an exam. If you're studying for an exam, remember, it's global versus regional. Global is cross-continent. Regional is same region only. Layer 4 versus layer 7. So TCP and SSL, those would be layer 4. HTTPS would be layer 7. CDN, remember, this only works with the HTTPS global load balancer. All right. Cross zone balancing distributes traffic evenly across zones. Health checks are required to remove unhealthy instances automatically. So here's a little tip. Google Load Balancing natively supports Cloud Run, Cloud Functions, and App Engine using serverless network endpoint groups, those NEGs. This means your front-end IP can route requests straight to containerized microservices with all the load balancing magic still intact. All right, Cloud CDN. Cloud CDN is Google Cloud's native content distribution layer built to work seamlessly with HTTPS load balancers. It's designed to cache content at edge nodes so users hit local copies, not distant servers. It speeds up websites and APIs, reducing round trip time and improving time to first byte, and then scales with demand. So it handles massive global traffic spikes without breaking a sweat. It's not just about speed. Cloud CDN also reduces backend load, improves availability, even helps you with cost optimization by minimizing expensive cross-regional traffic. So how it works. Okay. Talk to a typical lifecycle. Let's see. So let's walk through a typical lifecycle with the Cloud CDN, right? A user requests content from your site, say an image, JavaScript file, a web page. The request is routed through your global HTTPS load balancer. If the content already exists at the nearest edge cache, it's served instantly. No need to hit your backend. If it's not cached, which is a cache miss, Cloud CDN fetches it from your backend, serves it to the user, and stores a copy at the edge for future requests. This system intelligently manages what to cache and when to evict based on freshness, popularity, and configuration. So the benefits of Cloud CDN is that it's ultra low latency. Requests are answered by edge locations, not distant origins. It reduces backend load, so static content like images, CSS, JS, or videos is handled by edge servers. It improves global performance, so content reaches users all around the world in milliseconds. It's seamless SSL support. So this works with HTTPS using Google managed certificates and auto scaling. It automatically adjusts to global traffic with no manual tuning, and then integrate with identity aware proxy, IAP. This is for secure, authenticated edge delivery. All right. So pro tip for the exam, a tight load balancer integration. This must be used with HTTPS load balancers, not TCP or SSL proxy types. Cache invalidation. You can purge content manually or automate via API calls. Logging and monitoring. Integrates cloud logging and cloud monitoring for performance visibility. Signed URLs and cookies. This is to protect private content using signed access tokens. Cache control headers. Use cache control and expires headers to fine-tune caching behavior. So configuring the Cloud CDN. So here's a very simple thing. What you would do is create the HTTPS load balancer with at least one backend server, and then enable this on the Cloud CDN on that backend, let's say an S3 bucket. And then optionally, you can configure cache keys, signed URLs, or custom TTLS, right? Then you deploy and let Google handle global distribution, scale, and performance, right? So if you go for the storage bucket, there's all these different backend services. But the load balancer just takes too long to load, so we're not going to show it. So what happens to unpopular content? Not all content is in constant demand, and that's okay. Cloud CDN uses intelligent eviction policies when a cached object becomes cold, i.e. no longer requested. It's removed to make room for newer or more popular data. This ensures efficient use of Google's vast this ensures efficient use of Google's vast edge cache infrastructure without bloating your resource footprint. So what type of content works best? Typically static websites and assets like HTML, CSS, or JavaScript, video and image hosting, public APIs with heavy GET request traffic, progressive web apps like PWAs, high traffic e-commerce product pages. And remember, you don't have to serve everything through Cloud CDN. You can selectively cache only what matters based on cache keys and path rules. Right? So a real world use case would be imagine a mobile game company with users across 5 continents. By enabling Cloud CDN, they cache game assets like maps, skins, and UI elements at edge locations. The result, faster game load times, fewer drop sessions, happier players, and lower backend costs. So to wrap up, performance is the one benefit. Edge caching reduces latency and speeds up delivery. It supports HTTPS and integrates with IAP. It cuts down on egress and backend compute costs. Its monitoring is built in for visibility with cloud logging and monitoring. And it's easy to enable by just toggling Cloud CDN on your load balancer's backend. So it's not just about a performance, it's about experience, reliability, and scalability on the edge. Okay. All right, Cloud VPN. All right, so this will be a little bit. All right, so we've covered VPN peering. Sometimes your applications can live in two worlds, part in Google Cloud, part on-prem. Maybe you're migrating workloads gradually, or your compliance policies require that some systems never leave your own data center. Either way, they still need to talk. That's where Cloud VPN comes in. Google's secure, encrypted bridge between your on-premises network and your virtual private cloud. What is Cloud VPN? It creates a secure site-to-site IPsec tunnel, which is using industry standard protocols to encrypt traffic over the public internet. Think of it as a private lane in a digital highway, sealed off from prying eyes. This lets your systems communicate securely across environments, use private RFC 1918 IP space, and route internal traffic without exposing resources to the public internet. So why should you use Cloud VPN? It's ideal when you need a fast, cost-effective connection between GCP and on-prem. Your use case involves low to moderate bandwidth, up to 3 gigabits per second per tunnel. You're not ready for dedicated interconnect, but want secure communication now. You're testing or piloting hybrid deployments before scaling up. Think financial data syncing, backup replication, internal app integration, all with encryption in motion. So how it works. Let's see. I don't think it's here. No, it's not. Oops. No, it's not available on this. Oh, darn. That's okay. Okay, so how it works. At its heart, Cloud VPN uses a few simple building blocks. The cloud router, which handles routing announcements for dynamic VPNs. The VPN gateway, the entry point into your VPC for encrypted traffic. Tunnels, these are IPsec connections between your on-prem device and Google's gateway. Each tunnel connects 2 gateways, one on premises, one in GCP, and must agree on IKE v2 security policies, shared secrets, and routing protocols. Cloud VPN supports dynamic routing with BGP using Cloud Router, static routing for simpler use cases, and high availability VPN for production grade resilience, and redundant tunnels for failover across zones or regions. Okay, all right, so important constraints. Before you configure Cloud VPN, make sure to follow a few rules. The CIDR ranges of your on-prem and VPC subnets must not overlap. It supports site-to-site VPN only, so no support for individual client devices like laptops or phones. It uses only IPsec tunnels with AES 128 or AES 256 encryption. Each cloud VPN tunnel supports up to 250,000 packets per second and with throughput up to 3 gigabytes per second. High availability VPN can scale higher. So here's some exam tips, right? Um, Cloud VPN will be encrypted for IPsec. Cloud Interconnect will be unencrypted for private fiber. Cloud VPN setup time is minutes. Cloud Interconnect time setup is days to weeks. Cloud VPN throughput is up to 10 gigabits per second with high availability. Cloud Interconnect's throughput is up to 80 gigabits per second. Cloud VPN is ideal for low to moderate traffic with fast setup. Cloud Interconnect is good for large scale, high performance enterprise workloads. All right. So routing options explained. Cloud VPN supports two routing modes: static routing and dynamic routing. With static routing, you manually configure routes on both ends. It's simple, it's predictable. Dynamic routing uses Cloud Router with BGP, which is Border Gateway Protocol, which allows automatic route advertisement and failover if the tunnel goes down. All right. Dynamic routing is recommended for resilience and scalability, especially in multi-site deployments. All right. So the quickest way to do this is to get this working, you need the following things, right? You need to configure the tunnel, right, with providing the peer. So let's say you set this up for, let's say, high availability, right? So you create this with the tunnel, create the name, the network, region. All right. Uh, I don't want to create that gateway. Should add the VPN tunnels. Why isn't it letting me go to the next one? So you'd set up, okay, basically you configure the tunnel with the IP, the name, the network, set the cloud router, VP, and using BP, if you're using BGP, right? Then you create the custom routes that advertise and accept traffic between environments. So that'd be that hybrid situation. And then you'd match the IPsec settings and secrets and routing, right? So you can monitor the tunnel health, the latency, and packet drops directly in the Google Cloud Console or using cloud monitoring for alerts. So a use case example would be your organization runs PostgreSQL database in your on-prem data center, but your web app front end is hosted on GCP. You need to replicate data between the two securely and efficiently. Cloud VPN would let you create the encrypted tunnel, route database traffic over private IPs, avoid exposing your database to the public internet, and enable hybrid queries and migrations without sacrificing security. So the benefits of this for the exam: encryption. It's IPsec-based site-to-site tunnels. Routing. It supports static and dynamic via BGP. And then traffic type. Internal RFC 1918, encrypted over the internet. CIDR overlap is not allowed between GCP and on-prem. However, the client VPN is not supported. This is site-to-site only. And integration is that it works with Cloud Router for smart routing. Whether you're bridging cloud and legacy applications, seeking backups, or starting a migration, Cloud VPN is your gateway to hybrid infrastructure. Next up, Cloud Interconnect. As your organization scales, some questions become bigger. How do we move petabytes of data? How do we maintain sub-millisecond latency across clouds and colos? How do we reduce dependency on the public internet? This is where Cloud Interconnect comes in. This is Google's enterprise-grade solution for private, high bandwidth, and low latency network connectivity. Cloud Interconnect creates a dedicated connection between your infrastructure, whether it's on-prem or in a co-located data center, and Google's backbone. Unlike VPNs, which encrypt traffic over the public internet, Interconnect takes a different route, literally. So there's two flavors of Interconnect. These offer flexibility to match your budget, your timeline, and operational footprint. It's a dedicated interconnect, which is the gold standard. You establish a physical link from your network equipment to Google's edge. Available at Google's co-location facilities, aka interconnect locations. Each link supports 10 gigabytes per second or 100 gig, supports 10 to 100 gigabytes per second, and you can combine them for up to 80 gigabytes per second connection. All right, you're in full control. This is ideal for latency sensitive or compliance driven workloads like financial analytics, genomics pipelines, or media processing. So here's a use case, right? A multinational streaming platform would need to just deliver 4K video globally with minimal buffering and compliance control. Dedicated interconnect ensures that content enters Google's edge at a line rate without public internet exposure, right? And then there's partner interconnect. If you're not ready for the physical setup, you can use a service provider. So your cloud traffic would ride over a partner-managed path to Google. It's great for mid-sized businesses or remote geographies. This scales from 50 megabytes per second to 10 gigabytes per second per VLAN attachment. So you still get private connectivity without deploying your own routers in a colo. Think of it as choosing between leasing fiber and having someone else deliver it to your door. So why use Interconnect? If you need performance, security, and scale beyond what Google VPN provides, Cloud Interconnect is your answer. And we already talked about this. The differences include, all right, for Cloud VPN, it's encrypted, it's internet dependent, up to 10 gigabits per second. It's lower setup with higher egress fees and hybrid, and it's best for use cases that are hybrid pilots or for backup. Cloud Interconnect is unencrypted, but it's private. The latency is ultra low. The bandwidth is up to 80 gigabits per second dedicated, and then the cost is higher, but there's lower egress fees. The best use cases are for real-time sync, media, and compliance. Cloud Interconnect connects you to the same infrastructure that powers YouTube, search, and Gmail. It gives you direct access to Google services like BigQuery, cloud storage, AI, ML, APIs, and GKE clusters spread across regions. How it works. For dedicated interconnect, you would choose an interconnect location, work with your carrier to provision a circuit to that facility, order a cross-connect via Google, provision VLAN attachments in Google Cloud, and use Cloud Router to advertise BGP routes. All right. For partner interconnect, you choose a partner provider from Google's catalog. You request a VLAN attachment from via the partner, and Google provisions the rest. There's no co-location required. So here's a use case. Imagine you're migrating an on-prem Teradata warehouse to BigQuery with tens of terabytes per day flowing between systems. A standard VPN won't cut it. With dedicated interconnect, you establish a 100 gigabits per second data direct pipeline to your GCP region. It's faster, more secure, and cheaper per gigabyte than internet-based egress. And because it uses BGP dynamic routing, your traffic can reroute automatically if something fails. High availability built in. So on the exam, watch out for certain things. Dedicated interconnect is a physical connection at a Google facility with up to 80 gigabits per second. Partner interconnect is through a third-party provider. This is 50 megabits per second to 10 gigabits per second. Right? Is BGP required? Yes. Both options need Cloud Router with BGP. Encryption. It's not over the link. It relies on app layer encryption if needed. Compliance. This meets the needs for HIPAA, FedRAMP, and financial services, and more. So in summary, your workloads require massive data. In summary, if your workload requires massive data transfers, ultra low latency, private secure communication, predictable performance, then Cloud Interconnect is your direct line to Google Cloud, bypassing the public internet. It reduces costs and elevates your cloud architecture to enterprise grade. All right, so wrapping up, we've covered the foundations of cloud networking from the internal structure of VPCs and firewall rules to peering, private access, global load balancing, VPNs, and high-speed interconnects. Each of these components is essential for building resilient, secure, and efficient cloud architectures. Remember these key principles. VPCs are global, but subnets are regional, giving you both worldwide reach and local precision. Firewall rules control traffic flow, even within the same network. VPC peering enables private communication, but watch out for transitivity constraints. Private Google access lets private VMs access Google APIs without public exposure. Load balancers distribute traffic intelligently across regions, zones, or services. Cloud CDN caches content at the edge, improving performance and reducing costs. Cloud VPN creates encrypted tunnels for secure hybrid connectivity. Cloud Interconnect provides dedicated pathways for enterprise-grade performance. And as you continue your Google Cloud journey, remember that networking is the fabric that connects all your cloud resources. A well-designed network foundation ensures that your applications are not just functional, but fast, secure, and scalable. So let's see. All right, a couple of questions. If you need to allow private instances in your VPC to access Google APIs without public internet, what should you configure? Private Google access. Which load balancing project would you use to distribute HTTPS traffic globally with URL-based routing? You'd use the global HTTPS load balancer. Right? You have two separate VPC networks that need to communicate using internal IPs. What's the simplest solution? VPC peering. What is true about Google firewalls? They can be scoped by service account. Which networking product would you recommend for a large enterprise needing to transfer 50 plus terabytes of data daily between their data center and Google Cloud? Dedicated Interconnect. And that would conclude chapter 5. Next up, we'll be going to chapter 4. Sorry, that would conclude chapter 4. Next up will be chapter 5, Containers in the Cloud, orchestrating workloads with Kubernetes. But till then, I'm going to tear down my environment, and I will see you later.